Welcome to our unit on work and energy. I would expect you to be coming in with some previous knowledge of the concept of work in a physics sense. Work is a tricky word in the sense that we use it in a variety of ways in an everyday setting, but in physics it has a particular definition. It involves a force and a displacement and how those two are related to each other. So let's take a look at an example on the screen and how we can springboard from your current level of work knowledge to a more advanced level. The equation for work sums up nicely the things that are involved in calculating work in a physics sense. Okay, you need a force, you need a displacement, and you need some part of the force to be parallel to the motion. Okay, and that cosine theta is what picks out the parallel part. Notice the units, right? The units for force is newtons, the units for displacement meters, so that gives us units of Newton meters for work. But we decided to honor another dead physicist and give this Newton meter a new name, the joule, right? A joule is a Newton meter. Okay, so there are other units of work, like you could measure work in calories. Joules and calories are equivalent. Okay, in thermal physics, we use joules and calories interchangeably. They're not. It's not a one-to-one relationship. There are roughly 4 joules in a calorie. And also, there's another unit called the electron volt. Okay, it's used in nuclear physics. But for our purposes, we'll be focused on the joule. Look at the example on the right. You see a block being pulled in multiple directions. If there are multiple forces, multiple works can be done. Right? Each force does some work. So let's, what we need to do is we need to pick out the horizontal component, right? So for force A, it's only that part there, right? It's only the horizontal component of force A that's doing work, and that's positive work, right, because it's in the direction of motion. Whereas force B is doing some negative work because its horizontal component is opposite the direction of motion. Of course, I did not indicate, as I should have here, that the displacement, right, the displacement is to the right. Okay? So, and what we can also do is we can look at a concept called net work, right, which is just all of the works added up, okay? So that would be the work from this contribution plus the work from this contribution, okay? Notice there are other forces on here, right, like weight, okay? But because they are in the normal force, but because they are perpendicular to the direction of motion, right, cosine of 90 is 0, they do no work, right? So there can be forces acting on an object but not doing any work on it because of their orientation. All right, let's move to energy. Energy is a very abstract concept, right? If I ask you to show me some energy, it'd be kind of tough to do, but it's a very useful concept, and students seem to take to it easily. Energy is defined as the ability to do work, right? To the ability to exert a force through a particular distance. Okay, let's move on to something that has a very fancy name, but it's a very simple concept. It's called the work kinetic energy theorem. It relates the work that you do to an object to the change in kinetic energy of an object. You see here, pretty bad drawing, but you see an object being thrown right here. It starts in the hand, and here it's left the hand. Okay? And I think you would agree that there is work being done right through this motion here, right, as long as your hand is touching the ball. Okay, that would be a displacement, right? And, of course, there's a force from your hand. So we have force, we have displacement that are parallel to each other. We're doing work. Now, what happens as a result of you doing work to this object? What happens to its kinetic energy? Well, exactly. It speeds up, right? It changes its kinetic energy. So all work kinetic energy theorem is really a fancy word for a very simple object. A very simple concept, which is this: the work that you do on an object goes to change the kinetic energy of an object. It's basically the accounting, the energy accounting for when work is done, right? If you've done work on an object, you should be able to account for it. And the way you can account for it is by looking at the change in kinetic energy of the object, right? So if we are a little more explicit here, we can write that out this way, okay? But that's all the work kinetic energy theorem is. In a way, it's just another way of saying the conservation of energy, right? You're giving an account for the work that you've done by saying, hey, look, the kinetic energy of the object I worked on is now different. Work kinetic energy theory. All right. What happens, though, if you're trying to calculate work and you want to look at a situation where the force is changing, right? We have an equation that allows for only one force, one value. Well, I think you've picked up in this course, we've done this, we've come to this conundrum, this juncture several times before, which is how do we go from one value to a variety of values? And I think you know the answer. The answer is calculus, right? So this is where we springboard from your first year knowledge to your second year knowledge. I'll give you a moment to read the example on the board. It's an example of a spring acting on a block. You may want to pause to read the full extent of the problem, but what's happening here is we're pushing the block in this problem to the left, 8 centimeters. We want to know the work that's done by the spring during that time. Okay. First question to answer is the spring, while you push the block to the left, right? So maybe we should draw a hand here. Okay, that's you. While you push the block to the left, what kind of work is the spring doing? Positive, negative, or zero? I hope you can see that you're doing negative. Excuse me, the spring is doing negative work, right? Because the spring is pushing to the right, but the displacement is to the left. They are what we say anti-parallel, right? The force and the displacement are anti-parallel, or 180 degrees. If you do cosine 180 in the formula, you get a -1, right? Negative work. All right. The spring obeys what's called Hooke's law. Hooke's law is this equation right here, okay, where K is the stiffness of the spring, right? It's the spring constant here. The higher it is, the stiffer the spring. Well, I think you can see that this is a straight line graph, right? A straight line graph. So let's graph that right now. Maybe I'll put it a little bit fatter. It's going to look something like that, okay, except I want to do a nice straight line. Okay, it's going to look something like that. All right, that's the graph of the force over a variety of displacements, right? The more you compress or stretch the spring, the more the force is. Okay? So, we are going to use a useful springboard concept into calculus, which is the area under the curve. Okay, we're going to look at the area under the curve for this displacement. It's going to be this right here. Okay, it's going to be this region right here. Okay? It's a triangle shape. All right? Where the base, okay, I didn't draw it exact, but this is about a height of 40, okay, and then this is 0.08, right, 0.08 meters, okay. We can find the area of that particular shape, that triangle, 1/2 base times height. Okay, and I'm going to erase this again to get a little more space. You can see that the units of the area under the curve is the units of Newton meters. Okay. Notice I also put the negative 0.08 in there for the negative displacement, so it could show up as negative work to confirm what we had agreed upon earlier. So that's how you find the work done, negative 1.6 joules, right? And then, of course, you could turn around part B. The block is released. Find its speed when it returns to the equilibrium position. Okay. Well, that 1.6 joules of work, the spring is going to turn around and do the same amount of positive work, right? So we can use the work kinetic energy theorem, okay, where the 1.6 goes right here, and then you can just, I'm not going to work it out, but I'll just sort of set it up for you, where you can just plug in these values here and solve for the final speed, right? When you push the block back to the 8 centimeter mark, it's not moving, right? So the initial velocity would be 0. And then you're just solving this equation right here for velocity. So that's an example of how to deal with a variable force. I think you'll agree that's a pretty friendly variable force, right? A pretty friendly variable force. What about if the force doesn't seem so friendly like this right here? Right? What if it's just some function? Well, we're going to do what we've done previously with these types of graphs. We are going to break up the area under that curve because it's still going to have, right, whatever area we end up calculating, it's still going to have the units of Newton meters and therefore the units of work. We're going to break that up right into a bunch of thin rectangles, right, whose width is, you guessed it, dx, right, and we're going to let the width of those go to 0. And you can see that our expression for work now becomes an integral, right? Where this is the f, right, and this is the d, the displacement. Okay, so for any function of work, right, that's a displacement function of displacement, you can express the work done as an integral. All right, moving along here. What about moving from like one-dimensional motion, right, which is kind of what we've been doing up to this point, to three-dimensional, like 2- and 3-dimensional motion? Okay, well, we can handle that using our vector toolbox. Okay, I'm going to write the work equation here in a slightly different form. I'm going to write it in dot product form. It's called a dot product. It's a vector operation that you can do. Okay, and interesting thing about a dot product is that the product that you get is a scalar. Notice that work and energy are scalars, right? They don't have a direction associated with them. That's one of the things that makes them friendly to work with for both teachers and students. But let's look a little more closely at how a dot product works. Okay. So first of all, the example here, I traced a path that an object might be following in space, right? It doesn't look three-dimensional; it just looks two-dimensional, but trust me on that one. And let's just pick a spot here, like let's say, at this spot right here. Okay, it's moving in that direction, right? Tangent to the motion. So that would be the displacement, which we often use the letter S for displacement if it's general. And let's just say that there's some force acting on it in some other direction, right? That's not necessarily parallel to it, maybe just this way, right? Maybe the force is like that. Okay. How do we calculate the work in that situation? Well, we're going to have to do this thing called the dot product. Okay. So to understand how the dot product works, you need. I'm going to write out vector A here and vector B in its component forms. Okay, you see the vectors in their component form, right? I, J, K. That's not a lot of multiplying, right? You got like, what, 9 terms there, each of them times 3. Well, here's the cool thing. The dot product of two perpendicular vectors is 0. Right? So when you multiply, say, this one times that or times that, right? I times j, they're perpendicular, and it's just like the cosine of 90. They go away. So you end up with a much simpler form here, where basically a lot of those products cancel out. And of the 9 products that you possibly could have here, you only end up with 3 useful ones. Let me write those for you. Basically, only these products here are non-zero, right? That one, the 2 i's, and then the 2 j's, right? And then the 2 k's. Those are the only ones that end up being non-zero, so that your x component of your product, okay, would be this one here. Actually, I said that wrong. There is no component to the product, because remember the dot product is a scalar. So it just ends up being this right here. You're just going to multiply the x components and the y components together, and the z components if it's a 3-dimensional vector, and you're just going to add all of those up, right, and you're going to get one number, and that's going to be the dot product. That's how you find the dot product of a 3-dimensional vector. Let's look at an example. Okay, again, you might pause and read this. We can draw vectors to represent the displacement, right? It's going to be kind of like a third quadrant displacement, maybe something like that. And then maybe a different color here for the force. The force is in the second quadrant, okay, something like that. All right. And so what we can do is just apply this nifty new dot product situation, right? Work is the dot product of force times displacement. Okay, so I'm just going to write those out and dot product them and come up with a solution. Okay, I've written out the vectors, okay, and then I've grouped them by components, right? The I terms together, the J terms together. Hopefully you'll see that the product of these is Newton meters or joules, right? So here we just have negative 18 joules and minus 20 joules. Okay, so minus 38 joules, right? Negative work's being done on this on this object during this displacement, it appears. All right, final comments here. In 3 dimensions, okay, the work kinetic energy theorem still holds, except that when you put the velocity in, you have to put the total velocity, right? The total magnitude, not a component velocity in a particular direction. Just use the total velocity. And then the same integral still holds, right, for variable force, except we're just substituting the letter S for the letter X, right? S being the general 3D displacement. All right, there you have it, work and energy.